Okay, folks, we're going to do a second part to the screencast that I did previously, and that's some implications that come about from the Boltzmann distributions. Specifically, we're going to be talking about Graham's law and liquid vapor equilibrium. So, first thing that we're going to talk about is Graham's law of effusion and diffusion. So, here's some definitions. The difference between diffusion and effusion. They're pretty related. They both have to do with the motion of gases. Diffusion is the gradual mixing of gas molecules with other gas molecules. So if you put two gases in a container at opposite ends, they're gradually going to come and mix together. And effusion is the process by which a gas can move through a really small opening. This is why your tires gradually go flat, because there's really tiny openings through the rubber. It's not totally impermeable, and the gases can slowly wiggle their way through it. So obviously, since both of these factors deal with motion, either mixing of gas molecules or the molecules escaping through small holes, the velocity is going to have an important role. And when we're talking about velocity of gases, we're talking about Boltzmann's distribution. So just to review, y-axis is the percentage of the molecules that have a particular speed. X-axis is either the speed, or it's sometimes written as kinetic energy. And whatever the highest point on the graph here, that is approximately the average speed or the most probable speed. And the speed is a function of the mass and the temperature. That's the key thing to remember. That's why I put this up here. So anything that decreases the mass or increases the temperature is going to increase the velocity and therefore increase the rate of diffusion and effusion. So if we raise the temperature of the gas or we decrease its molar mass, say we switch from O2 to helium, that's going to increase the most probable speed, increase the rate of diffusion and effusion. And conversely, anything that lowers the temperature or increases the molar mass is going to do the opposite. Okay? So kind of a common question that you like to see about this is they'll have a tube. Usually they draw it, it sort of looks like a dog bone, and it's got like the halfway point there. And they specify that two gases are released simultaneously at either end of this tube, and the question is which one reaches the halfway point first. So which one is going to diffuse to the halfway point the quickest. And so we've got a molar mass here of 32 versus we've got a molar mass of 2. Temperature would be constant, so that doesn't matter in this situation. The lower the molar mass, the faster velocity. So helium would reach the midpoint faster than would oxygen gas. All right, that's kind of a typical question that you see about this. We can also put some numbers behind it though. So let's look at the actual equation for Graham's law. Excuse me, here it is. And what we have is rate 1 and rate 2. Those are the rates of diffusion or effusion for the respective gases. And they are related to their molar masses. And it's the square root of the molar masses. One thing to note is the rate is inversely proportional to the molar mass. So we have rate 1 in the numerator, but we have mass 1 in the denominator. And rate 2 in the denominator, mass 2 in the numerator. Some students get kind of lazy and they expect this to be rate 1 over rate 2 equals square root of mass 1 over mass 2, and that is not good because this is an inverse relationship. And you can solve this equation either absolutely or sort of relative rates, and we'll look at both of those here as an example. So the absolute solution is going to specify some particular rate of diffusion. And you'll know that it's a rate because it will have a time component. So we've got, under some conditions, hydrogen diffuses at a rate of 0.5 moles per hour. So half a mole is moving somewhere in an hour. And it wants to know what rate would carbon monoxide diffuse. So we would set this up, and let's call hydrogen gas 1, so it's going to be, mass 1 would be 2, and that means its rate is going to be rate 1, and carbon monoxide is gas 2, so mass 2, and it's going to be 12 plus 16, 28, and what we're solving for is the rate that carbon monoxide diffuses. So now it's plug and chug. 0.50 over R2 equals square root of, take note here, mass rate 1 on the top, mass 1 on the bottom, rate 2 on the bottom, mass 2 on the top, and solve. You can also do these kind of relatively, where they tell you that some gas would diffuse at twice the rate or half the rate or some percentage or some decimal fraction of the rate. And these are really just straightforward. What you have to realize is that they're actually giving you both rates, even though you only see one number. So if we're calling the unknown gas having a rate of 81.2% of hydrogen's sulfide, we actually have the rate of hydrogen sulfide also. It's just going to be 100%. So if we call this mass 1, and that's going to be 34, 100% is going to be rate 1. And then what we're looking for is what would be the mass of something that moves at 82%, 81.2% of that rate. And so we're looking for mass 2. So even though you only see two things in the problem, a rate and a formula, you still have everything that you need. Just know that call the other rate, or call the rate of the known gas 100%, or if it's giving it to you in like decimal fractions, call it 1. So we're going to plug numbers in. So 100% over 81.2 equals mass 2 over mass 1. And you would identify this gas by its molar mass. So either your answer choices would be specific molar masses, or it would be a range of gases, and you would select which one has that molar mass. And here's a website that has some calculations of both absolute and relative solutions. I suggest that you check it out. The other thing that we're going to talk about is liquid-vapor equilibrium. So we need to take a second to define exactly what equilibrium is. Dynamic equilibrium is a situation where we have two opposing changes that are occurring at the same rate. And so that means there is no net change. And so we need some reversible reaction. And what we're going to be looking at is we're going to be looking at specifically the liquid to gas equilibrium. And this is reversible. So the equilibrium occurs when the rate that the liquid is turning to gas is equal to the rate that the gas is turning back into liquid. Some of the misconceptions that students have about equilibrium is that changes stop occurring. The changes still occur, it's just because they're equal and opposite, there's no net change. So that's sort of the key thing right there. No net change, not that the reaction stops. It's just that both reactions are occurring at equal and opposite rates. So let's look at kind of an example to drive that home. I made up a fictitious situation here. I have 16 tiles. They're blue on one side and orange on the other. and we've got a reaction that is blue turns to orange, and it is reversible, so the orange can turn back to blue. But they have different chances of occurring. There's a 50% chance of blue turning to orange. So I set these up at each tile. I rolled a die, and if I rolled a 1, 2, or 3 on a blue tile, I changed it to orange. And orange turning back to blue has a 16 and 2/3% chance, a 1 in 6, to occur. So if I was at an orange tile, only if I rolled a 1 did I switch it back. So in the beginning here, you see all blue, and what happens is we have this, and I'm repeating this stepwise. But you notice here, once we get to step 6, even though the individual blue and orange tiles can change, I have 4 blue and 12 orange through all of these steps. So this would be the point where equilibrium has been reached. The changes are still occurring, but we've reached a stable equilibrium condition of 4 blues and 12 oranges. So we would say that under these conditions, the equilibrium favors orange, or we would say it favors the right side, or it favors the products. All of these things, we could use to describe this particular equilibrium. If I changed, my percentages up here, the likelihood that something happened, then, the equilibrium conditions would change, and maybe it favors blue. But in my little fictitious example, this is what I got. So let's put this in terms of our liquid vapor equilibrium. And so I want you guys to picture some, sealed up bottle that has some water in it. And that water is going to be evaporating. And then some of the water, once it's in the gas state, can be returning back to the liquid state. And we're going to reach some equilibrium where the amounts of gas and liquid stop changing. But how is it that we can have liquid molecules turning into gas molecules at temperatures below the boiling point? So let's say I set up this point. This is the kinetic energy when water boils. So that's the amount of energy that it has to overcome the intermolecular attractions between the liquid molecules and escape into the gas state. So you can see that right now the temperature is well below the boiling point. So how is it that we can have boiling occur? And it's because we've got this Boltzmann's distribution of molecules. There's always going to be some amount of liquid molecules that have enough kinetic energy to escape into the gas state. So if this is my situation for the liquid, this tail of the graph over here would be the molecules that possess enough kinetic energy to evaporate. And I could draw another one of these now for the gas state. And kind of the converse situation would happen. There's going to always be some amount of the gas state molecules that are at the lower end of the energy, and those are going to condense. So we have two opposing reactions, and there's always going to be some molecules that have enough energy to go from the liquid state into the gas state, and there's going to be some members of the gas state molecules that are at the lower end of that are going to return to the equilibrium. Depending on what we do to the kinetic energy, and shift these distributions, so as I raise the temperature, this most probable speed will shift further over, so I would get more molecules that can enter the liquid state. And then the same thing for the gas. As I raise the temperature, more of the molecules are going to be able to have enough energy to remain in the gas state. So we do have an equilibrium between liquid water and gaseous water, even at temperatures below the boiling point. So let's kind of look at what might happen initially with our equilibrium. So here's my bottle, and in the very beginning I pour some water into my bottle, so all of my molecules are in the liquid state. So 0 gas, 100% liquid. And as soon as I put them in there, those members on the high end of the Boltzmann's distribution are going to begin to escape into the gas state. A little bit less water, few here, and as I'm approaching equilibrium, let's call this maybe 95 and 5, I'm still going to be having liquid molecules escaping into the gas, but now I'm going to have some starting to make the return trip. But I've not yet reached equilibrium here in my example, because I had 3 liquid molecules leaving, here I have 2 leaving, and only 1 returning from the gas state. So still not quite equilibrium. And if I do one other situation here, we'll let this one be where equilibrium has been reached. Maybe we'll call this 92 and this 8. Equilibrium would have been reached when my number of molecules leaving the liquid equal the number of gas molecules returning to the liquid state. So here would be initial, and this would be once the equilibrium has been reached. So we're moving like this. One thing to note, if I attached I'm going to erase my Boltzmann's distribution. Will it let me? No, apparently it won't. If I attached one of those U-tubes on this, what we would see here is this would be equal because there's nothing in the gas state. And if I go over to my equilibrium condition and we attach this, now we have pressure of H2O. These points would not be equal, and the difference between them would be the vapor pressure. So this is actually how vapor pressure is measured. You allow a liquid and gas to reach equilibrium and have a U-tube connected on the side of it. And the difference between the initial condition with no gas and this situation where you've reached equilibrium, that's your vapor pressure. So now we're going to wrap this up and talking about, well, okay, fine, we've got an equilibrium. That's boring. What happens when we poke it? And it's a principle known as Le Chatelier's principle, and it says if you have a system in equilibrium and you disturb it, the equilibrium shifts to oppose that change. So in our liquid-gas equilibrium here, see, I called this 92 and 8. What happens if we start making some changes to it? So let's say we increase the temperature. How would that affect that? Hopefully you guys would say, well, if I increase the temperature, that's going to shift my Boltzmann's distribution to the right, which favors the gas. And so my new equilibrium would have more gas, or you could say less liquid. Right? What if I somehow shrunk the volume of my container? This is maybe a balloon, and I can compress it. Is decreasing the volume, is that going to favor the gas or the liquid? And hopefully common sense would tell you, because gases are really far spread apart, that decreasing the volume would make things return to the liquid state. This is also the same thing as saying increasing my pressure. Again, because gases are really far apart. So if you increase the pressure to our system here, you're going to end up with more liquid. Let's do one other thing talking about Le Chatelier. And let's say that we inject some liquid into our system. So we have H2O liquid goes to H2O gas, and we somehow add some more to the liquid state. Le Chatelier says that this is going to react by trying to undo that change, and so we would expect to see more evaporation occurring at the new equilibrium, because it is going to try and evaporate to remove some of the extra liquid that we added and convert it to a gas. Similarly, if you added gas, you would expect to see more condensation, because our system is going to try and act to remove the gas. All right, so that wraps this up. At this point, we're still dealing with equilibriums sort of conceptually, no math, just sort of, if I do this, how does it shift the equilibrium? But in times to come, we're going to be dealing with some actually very specific math for equilibrium. So it's imperative that you sort of get your head around what exactly it means to be a system in equilibrium, that there's two opposing changes that are equal and opposite, and get solid with that understanding before we start throwing some specific numbers with it. So enjoy your day. We'll talk to you later.